Hi and welcome back. Today we're going to be looking at the first of our videos on equilibrium. So let's get started. This is the last of our topics for Area of Study 2 to finalise Unit 3. So the key things you need to be able to do following this video are being able to define the characteristics of a closed or open system, understand that reactions are reversible and be able to explain this in terms of particle theory and collisions, define the conditions for equilibrium, and what is meant when we use the term dynamic equilibrium. So far, for much of our chemistry education, we've learnt that chemical reactions are irreversible, that the reactions only occur in one direction. When a reaction does only go in one direction or appears to go in 100% yield, we say that this reaction goes to completion or is irreversible. They're usually irreversible because the activation energy needed to reverse the reaction is too high, remembering that this is the activation energy from here to here is the EA of the forward reaction, whereas the EA of the reverse reaction is going to be much higher. It's going to be this value here. So for a lot of reactions, the activation energy required for that reaction to go won't happen spontaneously. Okay, it'll need a bit of help. We see that with electrolysis reactions. But so we see this with things like cooking or the burning of wood or fuel. We lose the products out into the environment. We can't necessarily get them to go in reverse. That old adage that you can't uncook an egg. Part of this has to do whether or not the system we're conducting the reaction in is open or closed. We can only reach equilibrium when we have a closed system, okay? So a closed system is represented by this diagram here in A, where the products and the reactants are unable to leave the system. It's in a closed system, we can't have matter or anything leaving the system. An open system we can see here, such as if we open up a Coke bottle and let out the gas, that becomes an open system. The gas can escape, so we are getting an exchange of both matter and energy. So with equilibrium, we're typically, and in most reactions in a chemistry lab where we have things occurring in a flask or a sealed flask, we're going to be dealing with a closed system. Okay, so where we seal things off, everything remains in the flask. And if this is the case, such a system where only energy can be transferred in and out, such as heat, we get equilibrium being able to be established. In an open system, we don't see equilibrium. We can look at this in terms of the Haber process, which is the process for which we manufacture ammonia. In this process, we take nitrogen and react it with 3 equivalents of hydrogen to produce ammonia. This is done worldwide on a large scale. And it basically says that we can react this and all we'll get is the product that we need. So if we take 1 mole of nitrogen, we'll get 3 mole of hydrogen, and we would expect 2 mole of ammonia to be produced. In reality, the reaction doesn't get to 2 mole of ammonia. We see the reaction stopping beforehand, and this has to do with equilibrium. Essentially, what happens is as we are producing or undergoing the forward reaction, we are producing ammonia. And it makes sense according to collision theory that these ammonia molecules will be able to collide within the flask as well. The higher the concentration of ammonia, the more of them there will be to collide, so the greater the chance of a reaction. And ammonia can actually undergo a decomposition reaction back into nitrogen and hydrogen, what we refer to as the reverse reaction. This can happen spontaneously. Okay, so as the reaction proceeds, we can increase the concentration of ammonia. As that concentration increases, we will start to see more of the reverse reaction. This is critical in industry because our profits depend on the yield of the reaction that we get. So equilibrium is something we need to take large consideration of when we're wanting to manufacture any chemical product, because depending on where the position of equilibrium sits, this may drastically affect our yield because it will set the maximum amount of product that can be produced. Essentially, what's happening when we reach equilibrium is when we reach the stage where the quantities of reactants and products remain unchanged. The analogy that's best for this is if you have someone who is moving up an escalator and they match their pace exactly with the escalator, they will appear to stay in place to any observer, even though they are still moving. So if our person on the escalator was to stop putting in effort to try and keep moving up, then they would just end up being carried down. And this can be related back to the idea of reactions that are occurring both in the forward and reverse rate at the same time. Okay, so both reactions are occurring, even if there doesn't seem to be a change that is visible to the eye. So we need to consider the impact that this would have on industry. And essentially, it comes down to our yield. Okay, remembering that our percentage yield is the amount of product that we get divided by the amount of product that we expected due to the stoichiometry of the equation turned into a percentage. So we want to maximize the yield. We want to get the most product we can for the least amount of money. This means that large amounts of unreacted starting material are going to be wasteful and costly because we're not converting those into products. We need to find ways in industry to manipulate the equilibrium so that we get the maximum product possible. So these are the things that we can look at. If we think about that for a chemical reaction to occur, the reactants have to collide with the correct orientation and energy equal to or greater than EA, then it's possible for any chemical reaction to be reversed as long as it can overcome the energy requirement for the EA of the reverse reaction. So reactions don't always proceed only in the forward direction. The products react to form the original reactants, and the forward and backwards reaction occur at the same time. Eventually, the products and reactants will form at the same rate, and this is what we call dynamic equilibrium. Dynamic indicating the idea of movement reminds us that it's not that the reaction has stopped, it's simply that it occurs in the forward and the reverse direction at the same time at the same rate. We represent this special state, equilibrium, with the double arrow, noting that the arrow is only a half arrow at the top and a half arrow at the bottom. It is not this. That is not an equilibrium arrow. It is a half arrow and a half arrow here. So we can represent this graphically by looking at the rates of the forward and the reverse processes. That is that we can see here for the forward reaction, the rate will decrease as the concentration of the reactants decreases, because as we use the reactants up, they will not be able to collide as frequently. We won't see as many successful collisions. However, over time, we will increase the concentration of product. So as the reaction progresses from left to right, we will increase the concentration of product, which means that the rate of the reverse reaction will increase. We will see a decrease and a corresponding increase, and then at equilibrium, we see a horizontal line, okay, which is indicating that the rate is not changing, and this point will be where the forward and the reverse reactions are occurring at exactly the same rate. This means that we have reached equilibrium. Concentration, however, can look a little bit different. The concentrations of the reactants and products will no longer change at equilibrium, but they do not need to be equal. What we will see is as the reaction progresses, the concentration of reactants will decrease steadily until it reaches equilibrium, and the concentration of products will increase steadily until it reaches equilibrium. These could be the same concentration. The product concentration could be higher than the reactant concentration, or the other way around. Of course, for industry, we want to end up where the product concentration is higher than the reactant concentration. So if we consider this again for the formation of ammonia, this means that steadily as the reaction progresses, we will decrease our concentration of N2 and H2, okay, and increase our concentration of ammonia. Remembering that the rate of the forward and reverse reaction will occur at the same rate once equilibrium has been established. Just a quick note on equilibrium being dynamic. This is something that you can often be asked to explain in an exam, and the idea that the forward and back reactions have not ceased, they occur simultaneously at the same rate. So this can be parallel to a fish swimming upstream and staying in place. The amounts and concentrations of the chemical substances remain constant. The total gas pressure is constant if gases are involved. Temperature is constant. The whole system remains constant, as though nothing is changing. However, the reactions are still occurring, even though there's no visible or discernible indication of this. The reaction is said to be incomplete in that all substances of the reactants and the products will be present in the reaction mixture at equilibrium. This means that we can see for colored reactions equilibrium being established. In some systems, we can observe the color change over time. The decomposition of N2O4 into NO2, which is a brown gas, is an example of this. We can start with N2O4, and as the reaction starts to proceed, it is a light brown yellowing color. As we produce more NO2, it gets darker, until eventually we will see no change in color because the equilibrium has been established. So we can follow equilibrium by seeing whether or not colors darken, or perhaps if there's two color states, which one is favored from one side to the other. So when we talk about equilibrium, we tend to refer to the extent of the reaction. This is to say how far to the right the equilibrium sits, how much of the forward reaction has gone. We refer to this as the equilibrium position, and this is how much, we can think of this as how much product is being obtained. It doesn't give us any information about how quickly it's reacting, but just how far it will go on the path towards completeness. So the rate of reaction tells us the change of concentration over time, so how fast we will get somewhere. The extent of reaction tells us how much product is formed when the system reaches equilibrium. And in the next few videos, we will look at how we represent this graphically, mathematically, and talk about how we can change the position of equilibrium in industry.